All right, welcome to The Explainer. So today we're going to dive into this really fascinating new theory, one that might finally explain why so many of our modern systems, the stock market, social media, why they all feel like they're just constantly on the verge of breaking. It's called Information-Coherence Theory, and it is a big one.
So let's just start with this mystery, right? It's something that really defines our modern world. I mean, we've built everything to be faster, more advanced, more connected. But why does all that speed so often just spiral into total chaos?
I mean, think about the financial markets, right? You've got these high-speed trading algorithms that can cause what's called a flash crash. We're talking billions of dollars vanishing in minutes, and there's no human even touching a button. It just happens.
Or you see it online all the time. A single comment may be taken the wrong way, and boom, it triggers this instantaneous, furious social media mob. It goes from a simple discussion to just absolute chaos in the blink of an eye. And believe it or not, you can even hear the same exact principle in something way simpler. You know that awful, high-pitched screech you get when a microphone gets too close to a speaker? That's feedback. The signal is feeding back on itself way too quickly, and the whole system just goes haywire.
Okay, so here's the thing. These aren't just random, unrelated glitches. According to this information-coherence theory, they are all symptoms of the exact same underlying problem. It's called the acceleration crisis.
So what's really interesting here is how the theory explains this. It argues that this isn't just about, some bad settings or a poor design. No, this is a fundamental law of thermodynamics, but applied to information. Wild, right?
To really get our heads around this, we need a new way to think about it, a pretty powerful metaphor. The theory asks us to imagine the delay in any feedback loop, the time it takes for a system to react to new information, as a kind of temperature.
Okay, so think about it like this. In the physical world, right? High temperature means molecules are just zipping around like crazy. Well, in the world of information, a high informational temperature means the feedback is nearly instant. And a cold system? Well, that's one with super long delays. It reacts very slowly.
And here is the crucial point. Both extremes are super dangerous. A system that's too hot, where the feedback is just way too fast, it overcorrects itself into total chaos. That's our screeching microphone. But a system that's too cold is just sluggish. It can't adapt to change, and it eventually just drifts into irrelevance.
All right, so this brings us right to the core idea of the theory, which actually gives us a way to measure and really understand this super delicate balance. And that measure is called coherence, represented by the Greek letter lambda. Honestly, you can just think of it as a stability score for literally any system. It's a way to quantify how well that system can hold itself together and, stick to its original purpose. And this coherence, it's not a static thing. It's the result of a constant tug-of-war between four really fundamental forces. On one side, you've got destabilizing pressure and this natural frictional decay just trying to pull everything apart. But fighting back, you have the system's own ability to heal, its restorative healing, and the corrective information it gets from all that feedback. So a system is stable, or coherent, only when its ability to heal and its corrective feedback are strong enough to perfectly balance out those forces of chaos and decay. If you get that balance even a little bit wrong, the whole system fails. Simple as that. Okay, now this is where the theory goes from interesting to absolutely breathtaking. It argues that this isn't just some rule for computers or financial markets. No, this is a universal law of nature.
The source material really puts it perfectly. It says that every stable system in the universe, from the absolute smallest to the largest, is constantly making this trade-off. It's burning energy to create predictability and order out of a totally chaotic world. And that feedback delay? That's the key variable in the whole equation.
And this just brilliantly shows you the sheer scope of this idea. We're talking about the same fundamental law that governs how neurons fire stably in your brain, also governing the metabolic balance in your body, the learning process of an AI, and even the climate regulation of the entire planet. It's wild. They all rely on feedback loops that have just the right amount of delay.
So what this all predicts is that for any given system, there's a sweet spot. There's this optimal delay time that allows for the absolute maximum stability and coherence. You could call it the Goldilocks zone of feedback. Not too hot, not too cold.
And this is why all of this really matters. Being too fast isn't always better. In fact, it can be just as destructive as being too slow. What the theory is telling us is that to achieve stability, you have to find that perfect rhythm where the system is responsive, yeah, but not reckless.
So, what's the ultimate takeaway here?
I mean, if this law is truly universal, if it applies to everything, can we actually measure it?
And remarkably, the theory says yes. It proposes that we can actually boil down this whole complex balance into a single fundamental constant, a number that could act as a universal rating for the health and stability of any system you can imagine.
It's called the Information-Coherence Constant, or lambda naught. And what it represents is the absolute bare minimum level of coherence a system needs to survive. It's the tipping point, the line in the sand between resilience and total collapse. I mean, just stop and think about what this means for a second. It suggests that one day we could develop tools to measure exactly how close any network, our economy, our power grid, even a social network, is to a catastrophic failure, all just by analyzing its feedback delays and how information flows through it. Insane.
And that leaves us with one last kind of provocative thought. Our modern world is completely obsessed with speed, right? Eliminating delay, maximizing efficiency. But if this theory is right, in our relentless pursuit of hotter and faster systems, we might be systematically destroying the very thing that keeps them stable. So the question is, have we forgotten how to be coherent?